com isso, prova muito a importância do programa INCT, que não só em bioanalítica, mas como em vários outros INCTs, a contribuição, a possibilidade de avanço da ciência no país, em função desse programa, acho que é imensurável. E ter a continuidade dos INCTs é fundamental para o avanço científico e tecnológico do país. E nesse momento, onde a gente está encerrando essa edição dos INCTs, a gente tem a grande esperança que o governo faça um novo edital e que ele está prometendo que esse ano vai ser lançado um edital para que a gente possa dar continuidade a esse programa de muito sucesso, que é inegável e que todos reconhecem o grande avanço que teve em função desse programa dos INCTs. E, naturalmente, a nossa bioanalítica deve continuar. E acredito que todo o sucesso que a gente conseguiu, a gente pode conseguir ainda mais, podendo fazer, né, toda a diferença para os avanços científicos do país. Então, acho que gostaria muito de poder contar com todos para que, durante a nossa escola, possam ser feitas discussões, possam ser feitas debates, para que a gente se prepare, para que a gente possa ter, no futuro, a continuidade do nosso INCT de bioanalítica. E acredito que vai ser um momento muito propício para que a gente possa discutir e ter realmente a possibilidade de ter uma reflexão para que a gente possa fazer uma proposta de continuidade, fazendo, né, todos os caminhos que devem ser feitos para que a gente possa atingir o nosso sucesso. Então, gostaria de agradecer muito a todos os palestrantes, não só os palestrantes convidados, que vão contribuir muito, né, com a questão da bioanalítica. Então, agradeço, né, muito a presença e a colaboração desses palestrantes que vão contribuir e muito durante a escola. Então, gostaria de agradecer a todos vocês pela presença e pela dedicação e importância que é dada para a Escola de Bioanalítica e, naturalmente, para a bioanalítica do país. Então, agradeço e espero que possa ser uma escola muito frutífera e que vocês possam desfrutar e possam, né, poder realmente aproveitar o momento para poder ter um conhecimento, né, sempre acrescentado e sempre importante na formação de cada um de vocês. Eu encerro aqui, desejando, então, uma boa escola para todos. E antes que eu esqueça, eu tenho que agradecer ao pessoal que possibilitou, né, a execução da escola aqui, que são os alunos que basicamente fizeram toda a preparação aí para que vocês possam ter esses dias, né, bem recebidos aqui no Instituto de Química para a escola. Então, eu agradeço toda a comissão, todos os alunos aí que fizeram toda essa organização, foram atrás de fazer a possibilidade de ter recursos com patrocínios para ter o coffee break e assim por diante para organizar a escola. Então, também agradeço a todos os alunos aí que fizeram, né, todo o esforço para organizar a escola. Então, era isso e boa escola a todos.
Agradecemos a presença dos componentes da mesa e os convidamos a ocupar lugar no auditório para darmos continuidade à programação. Já posso? Dando continuidade à programação, é uma grande satisfação, uma grande honra poder apresentar o nosso palestrante de abertura da escola, o Dr. Carlos Garcia, da Clemson University, Carolina do Sul, Estados Unidos. Antes de eu começar a apresentação, só um esclarecimento. Tínhamos tudo para termos aqui o Dr. Carlos presencialmente, participando da escola durante todo o período, só que devido ao apagão, né, o crash da internet, que está afetando vários voos ao longo do mundo, principalmente dos Estados Unidos, acabou causando cancelamento de voos e o Carlos tentou embarcar no domingo, né, mas não conseguiu e a remarcação do voo era só para o final da semana, então, infelizmente, ele não pôde estar aqui presente, mas, gentilmente, ele aceitou fazer a apresentação de forma virtual, então nós vamos ter o prazer de termos aqui o Carlos fazendo a sua apresentação. Bem, eu tomei a liberdade, né, de fazer a apresentação do Carlos em português, porque ele tem muitos vínculos aqui com o Brasil, ele entende muito bem o português e também eu vou poupá-los aí do meu inglês. Bem, o Dr. Carlos, ele é de nacionalidade argentina, ele fez sua graduação em Bioquímica pela Universidade Nacional de Córdoba, onde também obteve o título de doutor em Química. Depois ele foi para os Estados Unidos, onde realizou 2 estágios de pós-doutorado, o primeiro deles na Mississippi State University e, na sequência, na Colorado State University. Em 2004, o Dr. Carlos foi contratado como professor de Química Analítica na University of Texas, em San Antonio, onde foi promovido em 2010 a professor adjunto e associado, e em 2014 a full professor. Buscando novos desafios, o Dr. Carlos mudou-se para outra universidade, para Clemson University, onde ele se encontra atualmente, e desenvolve pesquisa e desenvolvimento e aplicações de dispositivos microfluídicos, nanomateriais, processos eletroquímicos, eletroforese capilar e desenvolvimento de integração de instrumentação, tanto de alta complexidade, como também dispositivos simples de baixo custo, por exemplo, usando substrato de papel, sempre visando codificação de analitos de relevância biológica e biomédica. Também atua no desenvolvimento de biocatalisadores e, mais recentemente, no emprego de inteligência artificial em química analítica. O Dr. Carlos possui mais de 100 artigos publicados em periódicos de grande relevância. Em 2018, ele foi eleito Fellow da Royal Society of Chemistry. Atualmente é editor-chefe do periódico Electrophoresis e também editor associado de outros 3 periódicos, a Nature Scientific Reports, Sensors and Diagnostics e da RSC Advances. O Dr. Carlos tem diversos prêmios e honrarias, eu não vou elencar aqui para não estender a introdução, mas são prêmios relacionados não só à pesquisa, mas também ao ensino e extensão. E como eu havia dito, ele tem diversas colaborações com grupos de pesquisa aqui no Brasil, aqui na Unicamp, na USP, na Universidade Federal de Goiás, CNPEM, e vários outros grupos ao longo aqui do Brasil. Na palestra de hoje, o Carlos vai abordar um assunto bastante badalado, um hot topic, né, que é inteligência artificial em química analítica. Tá? Carlos, I know how much you would like to be here, we as well, but unfortunately because of circumstances that out of our control, that wasn't possible. But on behalf of the organizing committee of the 90th Bioanalytics School, I'd like to thank you so much to quickly accepting to give us this lecture. And I'm sure that your participation, even virtually, will enrich our event. So thank you so much, and now you can go ahead.
Well, first of all, thank you so much. I cannot tell you how much I missed the opportunity to be there. I was watching the news today, and Delta is still struggling to catch up with all the flights. So I'm not the only one suffering for the shutdown. I also want to thank especially Docile, Fracassi, and Laura for the invitation. It's always good to go to Brazil, and especially to Campinas to go visit friends. So I owe you one. Let me share with you my presentation. I'm going to switch. Hopefully you can see the title. So today I will be talking, as Docile mentioned, about how we are using AI to solve analytical problems. The title we picked is the title of a review that we published a couple of years ago dealing with this particular topic. So before we get started, I just want to mention a few things that are important, a few reminders. As Docile mentioned, I was born in Argentina, and this is always a good opportunity to show my Brazilian friends how well we are doing in terms of soccer. So going back to the science, as many of you know, I'm in Clemson University. We are in South Carolina, in the upper part of South Carolina. We are as far south as you can go and still have the 4 seasons. Lots of outdoor activities. Is a great place to live. Is super safe. And the university is organized in 10 colleges, and we offer about 80 degrees for undergrads and about 110 degrees for grad school. We are in the top 20 or 21 best public schools in the US, and we are, of course, in the R1 category from the Carnegie Foundation in terms of research. As you probably know by now, our lab does a number of things, mostly dealing with analytical applications. And the overall goal is to develop simpler, faster, and more efficient analytical strategies. The thing that you're going to hear today deals mostly with materials, and you will see why. So today, we're going to be talking about nades. And I don't know how many of you know anything about nades, but nades are formed by mixing 2 solids at room temperature. And when you combine them, they form stable liquids at room temperature, stable as at least a week at room temperature, and they become transparent. So at the beginning, we thought this was almost like magic, but there's not really magic. This is just a thermodynamic non-ideality when there is a depression in the melting point due to a significant decrease in the activity coefficient. The good thing about these solvents, besides being a mixture of natural organic compounds, is that you can have them in a wide range of properties, and those properties can be typically linked to the chemical structure of the components selected to make them. And they are supported, this interaction is supported by hydrogen bonding. So in many regards, they are similar to ionic liquids. The main difference is that they are cheaper to make, they have much lower toxicity, and they can be liquid at room temperature, they offer low vapor pressure, and they have high solvation capabilities. And you will see that in a minute when we start talking about potential applications. We, in the lab, we have done a number of things dealing with nades. And I'm going to show you just 4 quick examples of papers that we have published dealing with nades, again, taking advantage of the wide range of properties and the possibility to use them to extract compounds, to do catalysis, to solubilize organic compounds, and in this case, in 2023, to solubilize and preserve the structure of enzymes. So in the first case, what we did was to make an interdigitated array, and where that array is connected via nades that we made with lactic acid, glucose, and water. And this is typically referred to as LGH. And again, this is a simple sensor fabricated by laser engraving of cardboard. And the conditions that we selected are here, again, to preserve most of the cardboard on the surface. And in this case, the weird thing is that, or the cool part is that the nades act as an electrolyte connecting the pins of the array. And because this nades is, again, preserved by hydrogen bonding, when you introduce a competitor, as in this case, for instance, ammonia, it competes with the glucose and causes a change in the number of hydrogens free that are available in that nades, and then increases the resistance. So in this particular case, what I'm showing you here is that this particular nades is not only selective to ammonia, but also sensitive enough to monitor, for instance, fish freshness. The second case, we demonstrated the possibility to make these nades on site by using just solar power. And then we made a range of these nades by heating with this solar pre-concentrator. And then we used that to extract chlorophyll from the leaves of grape trees. And again, because of the significant savings in terms of energy, this turns out to lead to an agree score of almost 0.9. In terms of maintaining the activity of enzymes, what we did is to make a polymer based nades. In this particular case was alginate, an alginate-based polymer that will also give us the opportunity to play with the spherification process. And what I'm showing you here is that these beads of alginate made with nades not only have a narrower distribution, but also the size that is better suited for our particular application. And then in those beads, we modify them with 3 different enzymes, galactose oxidase, glucose oxidase, and lactate oxidase. And we also put 3 different dyes, orthodenosine, aminopyridine, and then TMB. And we made 3 different biosensors that you see here working in real time. We think the main advantage of this is that you can, instead of putting your sample or your sample in the sensing solution, you can just dump a handful of these beads and follow their color development in your analyte. Most recently, we have also used a more hydrophobic nades, in this case, menthol and dodecanoic acid, that is also stable in water, and we use that to replace chloroform in the extraction of surfactants. This is particularly useful in a method called the methylene blue reactive substances method. And what we did is we mixed these nades with water samples, and we were able to capture by the complexation of these anionic surfactants with the methylene blue that is positively charged, and then they transfer that into the nades, and we do an extraction, and then we follow that with a cell phone. We can have not only really, really good selectivity, but also very good sensitivity, enough to measure the surfactants in water from the lakes and the streams that run through Clemson. So as you can probably see, these nades are incredibly useful for a number of things. And the main question that we had is that how can we decide what components should we mix in order to make a useful nades? So as you can see here in the title, it drips with irony. So because designing new nades should be relatively simple. You only need to select the correct hydrogen bond donor, and there are quite a few, the right hydrogen bond acceptor, and then mix them in the correct ratio. And just to give you an idea, if you have a database of about 200 examples, and you mix them in ratios between 1 and 10, you may only get 40 million possible combinations. That will take simply forever. And if we go with traditional and computational tools, we can get some of the properties or explain the formation of some of the nates that have been published, but we cannot make predictions on what are we going to get if we mix thiourea and histidine. So by that time, when we started thinking about this problem, it was right before COVID, when this guy that many of you know, Lucas Aires, he just finished his PhD in our lab, and we were stuck in our basements and without many things to do. So during one Zoom call, I asked Lucas if he knew anything about AI. Lucas said, well, just a little, but let me do some reading. So in a week or 2 weeks, we learned that robots are still cool toys. Showing you the picture of the first robot I got when I was, 5, 6. And we also learned that there were a lot of people trying to teach computers how to interact with humans. And in fact, there was something that called Smarter Child that had been released in 2001, which was able to process a little bit of language, and it was able to predict with some statistical significance some relationship between words and respond to cues that you prompt in a small chat window, and would give you answers about weather, flights, or some summary about news. So at the core of this, there's a thing called a natural language processing that was really, really immature at that time, but that quickly changed in 2017 when a thing called transformers was invented. These transformers are other new models that can process a much, much larger amount of data simultaneously, and more importantly, weigh parts of that sequence differently. This is called attention, but the important part is that it can give the opportunity for this model to start capturing meaning in that context. So by the time we started working on this in 2020, these transformers were already 3 years old, so there was lots of information about them and ways to implement them. And just so you know, this is behind ChatGPT that was born about in 2022. And this is the reason why ChatGPT can generate human-like text as an output. If you don't know how ChatGPT works, behind that chat window, what you have is a training process. In this case, the original input, where basically ChatGPT was able to roam the internet and learn from everything that was available, including websites, books, articles, and broke that massive amount of information into tokens, which are just little pieces of text that can be encoded into the vectors and then feed to the model that is this language model that I told you about. And after that, this model can make predictions and make the output. At the beginning, these outputs were already were reprocessed using humans that were telling the model, yes, this is okay, and no, this is not okay. And the more they did that, the more the model learned on how to interact with humans and how to better respond. We got to the point where ChatGPT, the newest version, is really, really, really good at answering these cues. And more importantly, now the latest version of ChatGPT, it's called Omni, was trained not only using text, but also sound and images. So to give you an idea, it can not only tell you how an apple looks, but how an apple may taste or how an apple may sound when you bite on them. Why am I telling you all these things? Because we have based our first work on this natural language processing. And the first thing that we needed to do was to try to move from the chemical world into the text world. And for that, we use this thing called SMILES. And I'll tell you more about this, but this is basically a summary of different possible interpretations or translations between chemistry and text. And from the 1D structure, we can go all the way to 3D structure. We decided to go with SMILES, which provides it's called 2.5 structure that is somewhere aligned with the text, but can also give you a little bit of that overall 3D structure that the computer can understand using the neural network approach. If you want to know more about the SMILES, it's basically a chain of letters without the hydrogens, and we just transform molecules into words and reactions as a paragraph. And just like when you text, your iPhone can predict what's most likely word that you will use next. This software will do the same thing and will predict a product. So knowing all those things, I'm going to tell you about 3 projects first. The first one is the review that we are not going to talk about, but you're more than welcome to check if you want to learn more about overall algorithm types or what are the possible learning models that are available for you to apply, and what type of data do you need, and what's the training cycle look like. So in our particular case, we're going to start working with predicting the formation of nades that you already know what they are using AI. So what do we want? We want to provide the algorithm a mixture of components, having these components different structures and different stoichiometric ratios, and ask the model if this particular mixture will form an unstable nades or not. So in order to do this, we train the algorithm as a classifier. That means the algorithm will be able to answer yes or no and give you a statistical probability based on the training process that has gone through. So the first thing that we did is to teach the model some basic chemistry. And for this, we used about 1 million reactions that are already encoded in a database of patents. And basically, what we are following is a loss function, which is calculated between the difference. If we calculate the average difference between the answer provided by the model as an output and the right answer. And if the loss function goes down, it means that the system is learning. Now, the good part is that or the bad part is that although the system is learning some chemistry, the amount of real chemistry that the model knows is very limited. What we typically say is that at this point, it's like taking General Chemistry 1, where you can explain some basic things, but nothing else. So after we train this model, and this is using the MIT augmented database for 1 million unlabeled reactions, what we did was to expose this model to our own database containing nades. We call that process fine-tuning, or is an additional learning step. We collected this database from the literature and now has about 2,000 or 3,000 examples of stable nades with the corresponding stability. And the problem is that everything that we were able to find in the literature are positive examples of nades. So everything that worked and formed stable nades was reported. And just like any other undergrad, we figured out that the model was just memorizing these answers. So because the model was trained only with stable nades, anything else that we ask the model to do will answer yes. this is unstable NADES, even though it was the wrong answer. So what we did is to provide or to implement a data augmentation where we've trained the model with additional number of negative or unstable NADES that we developed in the lab. The good part is that after this step, the model was actually learning and understanding these very, very fine interactions between the molecules. And what I'm showing you here is that how the augmentation strategy that we decided to implement was improving both the accuracy of the test and decreasing the loss function. This is just the number of augmented data sets or augmented examples that we provided to the model. Then we decided, because now making NADES is relatively simple for us, what we decided was to try to test the capabilities of this model to make new NADES. And for this, we picked pharmaceutical compounds. In this case, what I'm showing you is ibuprofen, which is a very, very well-known compound with pharmaceutical applications. Unfortunately, the clinical effect of ibuprofen is limited by the poor solubility of this compound in water. It's about 10% of the ibuprofen you take will be useful. The other 90% goes straight to the toilet. However, if we can make this ibuprofen, if we can complex this ibuprofen with other molecules and make an NADES that is liquid and stable at room temperature, we would not only be improving solubility, but also improving the bioavailability of this compound, meaning that your kids can take a much smaller dose of ibuprofen, get even better clinical effects, and minimize adverse effects. So what we did is to make about 1 million possible combinations. These are random combinations between ibuprofen and all the compounds we have in the database, and we fed them to the model. And in about 30 minutes, the model was able to evaluate every one of those combinations and gave us this histogram, where I'm showing you the number of mixtures versus the probability of formation. We focus our study in the very last group, the ones that are most likely to form a NADES or have highest probability, between 80 and 85%. And we put them in the table. These are the components, and these are the probabilities. We did not know if these NADES would actually form. So what we did with Lucas is to make them in the lab. And sure enough, out of those 10, we were able to form 8 new stable natural lipidectic solvents containing ibuprofen. Although the idea, the 80% probability for each one of those is not the same thing that saying if you make 10, you will form 8. The 80% is a good match for us to show you how statistics propagate into real examples. This one was actually made in the lab, and we tested with rats. And what I'm showing you here is that the ibuprofen, or the ibuprofen formulation in NADES in blue, has a much, much higher plasma concentration for a lot longer than the standard Motrin that we buy at the pharmacy. We also wanted to know if the model that now was able to understand a little bit about hydrogen bonding could be applied to a different system. And that's how we started working with antioxidants. Because antioxidants are super important in food chemistry. In fact, you are eating antioxidants pretty much every day to prevent rancidity, especially in food that contains fat. This is a picture of chocolate, but if you take any vegetable oil or you use any cosmetics, very likely you're exposing yourself to antibiotics. The beauty of this is that some of these compounds can be combined and those combinations will lead to synergistic interactions. And again, if you consider that there are about 60,000 molecules reported with antioxidant properties, this will give you about 10 to the 15 possible combinations. Again, it's impossible for a human to try to cover this experimental landscape. So what we needed was to understand or to know if our algorithm would be able to predict the effect of mixing several antioxidants, knowing that the outcome could be either a synergistic interaction where the overall antioxidant effect is much larger than what you would expect from just a mixture, additive when there's just an addition, or even antagonistic when you mix two antioxidants and the overall effect is worse than what you would expect. And to give you an idea of the complexity of this problem, we put together a database and we did some analysis. About only 31 or 30% of those combinations will give you synergistic interactions. And these are the two different metrics that have been reported, but the number is about the same. It's about 1/3 of them. So your chances of hitting by randomly mixing antioxidants are very low. More importantly, if you start picking antioxidants, for instance, 20% of those antioxidants are present in the three categories in synergistic, giving you synergistic, antagonistic, and additive interactions, pointing to the importance of having the right pair and not just the right molecules. And the other important part is that not every paper reports the same methodology, the same sample, the same conditions. So trying to really understand what is going on with these antioxidants is quite complicated. We try to mix or to link chemical structure with behavior. And for instance, what I'm showing you here is molecular weight or hydrophobicity. And again, we were not able to link any of those properties with the overall effect. However, one of the things that we computed was the number of potential hydrogen bond sites of these mixtures. And what we found is that synergistic mixtures have a much higher chance of forming hydrogen bonding, just like the NADES problem, giving us a tremendous opportunity to translate everything that we knew from NADES to a whole new system. So now, instead of just predicting if the mixture will be a stable NADES or not, what we did was to train the AI model as a regressor. So it will calculate a score number, and then we can relate that score number. If it's lower than 85, we would consider that to have a synergistic interaction. If it was between 85 and 1.1, we would consider it that it will be additive, or higher than 1.1, it will be antagonistic. For this, we repeated the same thing, and if you go back to the first slide, or one of the first slides when I showed you about ChatGPT, you will start recognizing the same steps. Is a basic training step that we did with the foundational chemistry model, and then we selected a particular model to process that information. In this case, we call them regressors. And then we do some fine-tuning with the database, and then we start comparing the results that we predict versus the results in the database. That is the training step, or checking during the training step using the test and the trained data set, which is a subgroup of this data set that we assembled. And as you can see here, there is some correlation. We have still dispersion, but clearly the model is able to understand these small interactions. The next step was, of course, to try to understand if these interactions can be experimentally reproduced. So what we did in the lab was to select the test. In this case, it's called the T-bars test. It is just a quick test that will only target the formation of reactive aldehydes. And we compared, again, using mixtures of various compounds, how much T-bars these compounds or these oils will develop. For this, we used isobol curves, and that we can calculate how much the overall T-bars will be and compare that to the additive behavior. If we have more oxidation than we expected, we think we analyze that as an antagonistic interaction between the antioxidants. And if we have less T-bars or less oxidation than we expected, we consider the interaction to be synergistic. To give an idea, we did over 200 possible combinations using just 10 antioxidants in 3 molar ratios, and using, in this particular case, a commercial oil sample. And then we plotted the data, and what I'm showing you here is 2 different molar ratios, trying to show you that it's really hard to predict any interaction between these antioxidants by just looking at the T-bars or the oxidation amount. So what we did is to ask our algorithm if that is possible to do with these 10 new antioxidants that the system had never seen. And unfortunately, the system was not able to predict the interactions of these new antioxidants. However, if we start feeding some of that information back to the algorithm, we would be teaching the algorithm what's the relationship between the antioxidant power and the structure of these 10 antioxidants that are now being fed to the model. And what I'm showing you here is that by feeding just 21% of those 200 mixtures, we start to see some correlation. If we feed about 180 of those compounds, of those mixtures, we can now have an R-squared of 0.9, meaning that we can correctly predict about 90% of the behavior of 90% of those mixtures. So, as of today, or as of right now, you can probably see how important these SMILES notations are to represent chemical structures into words, and having these natural language processing models analyze those words to predict what's going to happen. But as I showed you before, the amount of information or chemical information that we can feed to the model is relatively small. So what alternatives do we have to teach more chemistry to our model? And in this particular case, I'm showing you a few of those variables that we are considering. And you can see that it would be impossible to represent these variables by a single word. So to solve this problem, what we did is to switch the representation. And instead of just using a word, we are now calculating a vector that includes multiple features for each one of these molecules. So what we do is we take the input as a SMILES notation, and we extract information from another database that is public. And we can calculate, or we can extract information as molecular weight. We can calculate, or we can extract hydrophobicity, number of hydrogen bonds. We can calculate, or we can extract acid constants, all this information is already in that database, and we're just coding it into a new vector that we can feed to the model and then process it either as a regressor or a classifier as an output. the cool part about this process is that we can not only do the forward step, but we can also walk backwards. And if we have one particular antioxidant that we are looking for, we can calculate the structure that that antioxidant should have. So now one of the things that we are doing is working with an organic chemist, so we can do synthesis of molecules with specific structures that will give us the answers that we are looking for. So in order to process this, what we did is to select the new model, no longer using natural language processing. And what we are doing is calculating a vector that contains about or more than 2,000 variables and analyzing that vector with a model called a gradient boost model. This model is not only really good at processing those vectors, but it's also good at doing one thing that we call transfer learning. And I'll show you why that is important in a minute. So what we are going to do, again, is to evaluate how this model is learning by following the loss function. And what I'm showing you here is, again, the 3 data sets that we selected. We have a huge data set, and we take about 85% of them for the training, 15% for the test, and out of those, we take 1/3, about 5% of them for the validation. And the idea is that the model will only see answers for the train, and then for the other 2, we keep those answers reserved so we can ask the model to make predictions and then make comparisons. What I'm showing you here is how we are using this model to predict melting points of these deep eutectic solvents. And the results I'm showing you here is for the training data set, and for the test data set, of course, has less data points, but it's doing really, really well. The other thing that is important is that we saw that now we have an extended range for these calculations. And even though most of the melting points that we are interested in are around room temperature, now we can start collecting or predicting information for a much wider number of deep eutectic solvents. We also found that at the very end of those curves, the error was larger. And the main problem is, how do we know what's going on or which ones are the culprits of those outliers? So what we decided to do was to actually go back to the database and pick them. And what we found is that the melting points for these compounds are outside the normal range for these deep eutectic solvents. So even though the system is learning most from the compounds that are most often presented to the model. The other cool part about these gradient boosting models and the vectorization process is that we can also analyze what is the feature relevance or the relevance of each one of those variables, each one of those vectors that we coded into each molecule. So what I'm showing you here is how much impact will have on the model output the ratio of the compounds, the initial melting temperature of the components, the molecular weight, or the number of atoms that each one of those molecules have. The important part of this is that we were able to identify in the molecular fingerprints the presence of OH groups, the presence of amines, and the presence of chloride as some of the most important components in those or functional groups on those molecules, defining not only the formation of the names, but also in the prediction of the melting point. Just like I mentioned before, the boosting or the gradient boosting model is able to do one thing that we call transfer learning. What does it mean? It means that, for instance, you learn French, and the model is able, with the same structure, able to speak Italian. So what we did is to train the model using deep eutectic solvents based on organic molecules, and we are trying now to apply this information to predict the melting point of a new group of deaths based on halogen bonding that the model has never seen. The other cool part about these halogen-based deaths, from the chemical standpoint, is that they are a lot more hydrophobic. So now we can start doing extractions with solvents that have much higher, or potentially much higher, extraction capacity. And as you can see here in the data set that we have collected in the lab, these are also weird because they form co-crystals. That means instead of having just one deep eutectic point or eutectic point, they will have two. So clearly, this will impose a challenge to our machine learning approach. In fact, if we try to predict the melting points of two of these compounds, we saw that we can actually predict part of it, but not the second eutectic point. So what we did is we went back to the data set and we took the green ones and we used these as examples so the model can learn the new chemistry that is involved in the halogen bonding and is not related to the hydrogen bonding. The gray one we took out and we used the one that is marked in orange as a test. And what we saw is that after showing the model these few more examples, the accuracy of the prediction went up to almost 98%, also allowing us to identify what are the most important features in the prediction of the melting point that now offers a difference of only 2 Kelvin with respect to the experimental values. So hopefully by now you have learned how we moved from about 3 or 4 years ago from an approach dealing with no artificial intelligence to try to start a new project and writing the first review that we published on this, on taking the leap between analytical chemistry and AI, and then moving into the prediction of the natural deep eutectic solvents, and then the prediction of antioxidant interactions, and now doing the gradient boosting model to predict properties of these deaths, including the melting point. There are a couple of things that are important to mention here. First of all, how much more complex the information is that we are feeding to the model. So we went from using smiles, which is text in 1D format, and using as a binary classifier to use the same information and then calculate and score using what is called a regressor. And again, we're using transformers for this. And then moving from the smiles to the fingerprints using the XBoost. The other important part is that if we go back to the first example that I told you, in order to make accurate predictions, we had to provide the model or to implement the augmentation, the data augmentation strategy, including about 1 million examples of random mixtures that we made in the lab, giving us an overall accuracy of about 82%. The next step that we took, that we implemented, we only used 200 examples, and the accuracy went up 10% to 92%. To now, where we're providing a lot more chemical information, we only needed 40 examples in order to bring the accuracy to 98%. So this is showing you how much the technology has improved in just a few years and how much faster these models are learning. I think at a pace where no human can possibly compete. I just need to mention the people that actually have worked with us on these projects. Most of these was led by Lucas, who graduated from the University of Sao Paulo. But a whole bunch of other people have contributed. And you may recognize this guy that is now in the lab, Wagner, who is the co-author of the last paper I mentioned to you regarding the extraction of surfactants. Funding for this project provided by all these people, very generous. And again, I could not be happier to thank Docil, Fracassi, and Laura for the invitation. Again, I'm really, really sorry for not being there. I'll be more than happy to open the floor to any questions, and if you need any help, I'll be more than happy to answer your emails. If you have any papers that you would like to share about sensors or diagnostics, please consider our journal, which is a gold open access. Again, thank you so much, and please, I'll be more than happy to answer your questions.
Thanks, Carlos. I'm quite sure that you show that picture with the Argentina team.
Of course.
Can you answer some questions from the audience? Questions? Someone? People are shy.
Do you have any questions, Docil?
I don't know. Carlos, can you hear me? Oh, okay. Any question? Carlos, I have one. Can you? Oh, okay.
Carlos, okay. Are you hearing? Very nice.
Thank you.
Wonderful. Indeed. So I enjoyed a lot your work on synergism and antagonism. But to be an antioxidant, there are plenty of mechanisms. And how do you do with, for instance, the atom transfer or complexation or something more on the biological part? Because there are receptors and several other mechanisms that depends more on interactions with some particles, nuclear factors, and so on. Have you thought about that, or only the chemical part, more directed to what you know about antioxidants? Okay, more in lab, but they are more biological sense in terms of antioxidants.
Well, first of all, thanks for the great question. In fact, you are 100% correct in the sense that we have thought about this in terms of other variables. One of the things that I'm particularly interested in considering is the redox potential of each one of these molecules that I think is going to have a tremendous effect on our capacity to predict antioxidant power. The other thing that is important to mention is that these models were trained to predict antioxidant interactions only. And the mechanism for those interactions could be electrostatic, could be hydrophobic, could be hydrogen bonding. Out of all those possible ways to link these two molecules together, it looks like, at least from the data that we have, it looks like hydrogen bonding plays a very important role. I cannot lie to you and tell you that this is the only variable that determines interaction or determines synergism, because it's not true. In fact, if you take some of these synergistic mixtures with high number of hydrogen bonding, not all of them, sorry, let me go back. If you take molecules that have high number of hydrogen bond sites, not all of them are synergistic. So the beauty of this is that the algorithm can still predict some of these. Again, with an 80 or 90% accuracy, I think in order to push that to 95 or 98%, we must include other variables. As you mentioned, for instance, the mechanism, the reaction mechanism would be incredibly important. So I'm not sure if I answered your question or was more like a comment to your question.
Carlos, I have one. Are you planning to use this method for separation science? For example, capillary electrophoresis, some interactions that are difficult to prevent using other softwares. But what do you think about?
We tried. That is a really good question. And the beauty of CE, for instance, is the simplicity. The challenge for CE is the simplicity, because in order to make predictions, you really need to train the algorithm. It's not just teaching, it's training. Think about this as going to the gym. You just don't get healthy if you go a few times to the gym. You need to systematically go for a long time. So in our case, to make these very simple predictions, we need a database of about 2,000 entries. That is the absolute minimum. So when you go to CE and you start considering not only electroosmotic flow, but charge to mass ratios, interactions with the buffer, interactions with the walls, interactions with secondary complexing agents, I think you will have to build a database of tens of thousands of examples. And only after that we can start thinking about training a model and start challenging that model with new separations. If you have a student that is willing to do that work, please let me know. I'll be more than happy to work with you and the student. But in the meantime, what I can tell you is that there are new models that can actually read papers and extract that information. They are too green for us, but they are popping up in the literature. So I think at some point, we would be able to have these models just read everything that has been published in a couple of days and give us an Excel file. Until then,
okay, thank you.
I owe you the C.
Any other question? Oh. Oh.
Hello, Carlos. Can you hear me?
Loud and clear, Laura.
Well, I heard some time ago that people are digitalizing some text to input for artificial intelligence. And I was thinking about that this is possible in the case of chemistry, that teach the AI to learn basic chemistry to do this kind of interactions and input papers for this. And if it's possible, we will lose our jobs.
Alberto, I doubt we will lose our jobs. These models can only predict things that they have seen before, or systems that they are familiar with. Your creativity, your capacity to identify new problems is unique and is 100% human. When you go to the lab and have that gut feeling that an experiment is going to work, well, computers do not have guts yet. So I think we are still ahead in this world of creativity, of intuition. Now, if you are thinking about evaluating your students only on their capacity to gain and retain information, I think those students are going to be dead very soon. As long as we can teach them to think and to solve problems, humans will still remain ahead. So we'll have jobs.
No questions? Oh, Lauro.
Thank you, Carlos, for nice presentation. And I would like to know if we put some wrong data in the model, what's the result? The result will be good or will be bad? And if the AI is very smart to give a result, that's important to put or to feed the model with the very correct data. If the data is not correct, of course, the result is not correct. And in the real world, when we have different situations that we don't have any pure compounds or just compound that we are considering, we have many other compounds in the medium. And what's the effect of these other compounds in the results if you consider only the some compound that you contain in the sample?
Laura, very good question. Just like anything else, I go by GIGO, garbage in, garbage out. If we train the model with wrong data, it will learn the wrong things. In fact, I did not tell you this, but in the first paper that we published, we had a number of data points that we got from papers that were published. But then we found out that those data points were wrong. There are mistakes in those papers. The good thing is that now we can do an analysis of the data set and see which points are weird. So that's what we did in this particular paper and the data that I'm showing you here, trying to identify those outliers, learning why the model is not understanding the behavior of these particular molecules. In this case, the answer is simple. It's because their melting points are on the extreme of, are on the extreme of this curve. But in some other cases, the data points are just wrong. Those will mess up the learning process. It would be equivalent, like in your class, instead of using a book to tell students to go read Wikipedia. They will learn the wrong things. A big part of this process is not only assembling the database, but curating the database. Where you go, or somebody goes and checks that the information in that database is correct. That's why I told you that these new algorithms that can extract information directly from the papers automatically, they are too green for us. But there are lots of things you can do in order to not only extract, but also filter that information, or put another layer in which you only consider things that are reported, I don't know, 2 times or 3 times. So there is a possibility to automate some of these processes and to increase the confidence of your predictions. Of course, the more you do, the higher the energy cost, the time, and the better the results. But one step at a time for us.
Hello, Carlos. My name is Gabriel. I'm a second-year student, and I'm a little bit nervous, so maybe my English is a little bit bad right now. But this last semester, I was studying organic chemistry with a teacher, and this teacher was trying to improve us some AI to help us with questions like lessons. So but when he selected a few books, and the AI only used these books to help us, to answer us. But the quality of the answers was pretty bad. And I want to ask you, how much time did you work teaching your AI? Because we used this AI for like a semester, 6 months, and we didn't see any improvement.
Gabriel, that's a really good question. I have to mention a few more details regarding the training step. We used the Palmetto cluster. That is the supercomputer here in Clemson. I think it's the 6th or 5th fastest computer in the world. And the initial training took us 3 weeks. The amount of information that you need to provide to these algorithms is enormous. And it's not just one cycle, but how many cycles do you present this information? These iterations is exactly that. It's how many times you present the information and you learn, or you let the algorithm develop the path in the network to find the correct answers, or to adjust the equations to get the correct answers. In this case, I'm showing you that with about 1,000 of those interactions or epochs, the computer can actually learn. But the amount of work that this takes is tremendous. I don't think you can get meaningful data if you start from scratch and you just feed 4 books. That's why the powers of ChatGPT is that it was allowed to read everything on the internet for months. And that's why it got so good at answering simple questions. Now, the bad part of this is that the amount of energy, for instance, that took for that computer to do the training process is equivalent to the amount of energy that will take for you to drive to the moon and back. I think it's like 8 times. So it's a very slow and tedious and energy intensive process. I don't know anything about the experiment that you guys did in that class, but there are already available pre-trained models that you can use for organic chemistry. These million reactions are organic reactions. And if you're specifically interested in getting a few of those examples, shoot me an email. I'll be more than happy to share some of those papers or put you in contact with somebody who can help you with those.
Carlos, I just have maybe a forecast question. What do you think about the future of AI in analytical chemistry? Just looking for a signal of the analyte in the sample to determine the quantity or the species. But in the future, do you think it's will be necessary or not using AI? Because just measuring some parameters like melting point or some other properties maybe will be easy to measure, and then get the information that is possible to determine the amount of the components of the sample. What do you think?
I think the answer to your question is it depends. There are things that will remain simple and probably outside AI. So, for instance, there is no point of including AI in a pH meter. Now, if you have to analyze metabolomic data, like Valeria is doing, the volume of information that you need to process and the possibility of processing simultaneously that information, considering not only peak number 4 or the charge mass ratio of 300, I think that's where the richness of the algorithm is. I think at some point you will start seeing more and more AI solving these problems or helping people solve these problems. But at some point there is a trade-off between complexity and cost versus the amount of information you need. So high end, I think definitely will see an improvement. The low end, like, probably more difficult. But on the other side, the possibility of reading text or calculating color intensity or doing these things more objectively can also help simple things like micropaths. Who knows? But what I can tell you is that this is a very, very exciting time to be doing chemistry and AI. If you're not doing it, you're probably missing a big chunk of it. So I encourage everybody to start at least paying attention to these papers, because you will need them to get a real job very, very soon.
John. Students? No questions. So, Carlos, thank you so much for your talk. It's a wonderful talk. And soon we can talk about this AI. This is an issue that I like. I plan to work with. And I hope next time you can have less trouble to come to Brazil. Okay.
Tell me about it. Thank you so much, everybody, for coming. It's great. I miss you.
Just a minute. Então, nós vamos finalizar essa primeira parte da escola, no período da manhã, e nós retornamos às 14 horas, mas antes, vamos agradecer novamente o nosso palestrante, Carlos. Então, voltamos às 14 horas.
Só um pouquinho, pessoal, bom dia. Vou dar alguns informes em relação à presença. Toda vez que vocês entrarem no auditório, vai estar a lista de presença com QR Code no PowerPoint, então vai ter da manhã e da tarde cada dia, e também na porta de entrada tem um QR Code, a lista de presença. Então é um formulário com nome para a gente ter o controle depois. Em relação a hoje à noite, nós vamos ter uma confraternização que foi preparada com uma forma bastante especial para todos os participantes. Todo mundo está convidado, cada participante recebe ou um chopp ou um